So now we're going to shift gears and we're going to start talking about thin airfoil wings. When I talk about thin airfoil wings, I'm really not talking about they are strictly equal to zero, the thickness is zero. What we are talking mainly is that and the cord wise length compared to the thickness is very small. So in essence, it's very small. We can take it equal to zero. By doing that type of approximation, we can significantly reduce and simplify our analysis. And in the preliminary design analysis, we use thin wall airfoil structures all the time because they simplify our studies. Now, for more rigorous analysis, we have to consider the thickness as it is, but we will lay out the foundation for that later. To do that, let's begin our discussion here with the Kutta condition. When we talk about the Kutta condition, we are basically talking about the following. So let me change the colors here very quick. So when you have a flow, right, you have, oops. So you have a flow coming in this direction. That flow is going to intercept your airfoil. The airfoil is going to have 2 points, right? You're going to have a point there and a point there. And if the flow looks like this is a high, it's a high angle of attack. This is a low angle of attack. So here in this particular case, your stagnation points will be here and point there. The points 1 and 2 is the location where your kinetic energy is equal to 0. Okay, so the points 1 and 2, these points are your stagnation points where you will have absolutely no velocity. Now, the consequence of this is when we assume this, and we're going to assume, so one of the assumptions is, and actually a very good assumption, that when you have a flow around this, you have some sort of circulation, right? You're going to have one specific circulation. It's going to give you one value of lift. But the problem that we're going to have is that because of our analysis, especially thin wall analysis, thin airfoil analysis, what the analysis suggests is that you're going to have an infinite number of solutions. And this is really not possible. It is going to bring a big dilemma there because I can only have a single value for lift for every circulation. I'm going to have one value of lift, not multiple values of lift. For this is going to suggest if I have a circulation, I have an infinite number, and that's not possible. So let's understand this concept a little bit better. So if I consider the case of an airfoil where the airfoil is just starting, this is the early on, let's say time equal to 0, when the flow is, or the airfoil is just starting, your plane is just starting to take off, is starting to move, so your velocity is very low, and look what happens here. Your velocity does something like this, right? This is the shape of your velocity, and this gives all the your trailing. You had this cusp over here, and this is going to bring you some problems there at the beginning. You have sharp corners. However, as the velocity keeps accelerating, right, as you and let's say another time t1, you keep increasing. In this immediate stage, you can see that you start developing now a specific stagnation point. Okay, so what happens at the top and what happens at the bottom, eventually what's happening, the flow is becoming a little more uniform. And as you keep on moving, and it becomes, let's say, another time t2, where your flow is fully developed, now you can see what's happening here is fully developed, so it looks something like this. And this is the nature of the Kutta condition. Okay, so the Kutta condition basically is stating that that your flow going outside of point 1, there will be only one stagnation point there. And to better understand what's really happening here, let's consider a couple of scenarios. First scenario is, let's suppose we have a sharp edge, right? Maybe a case like this, we got this sharp edge. What do I do with a sharp edge? Well, you have really not many options here, because if you have a sharp edge, now you're going to have a velocity coming from here going in this direction, and let's call this velocity v2. And the velocity from the upper surface is going to come in this direction. Let's call that velocity v2. Now, v1, sorry. And now, what we really know is that in order to be single value, the value of the velocity leaving this point has to be completely, they have to be the same, but at this point they have to be 0. So the only other possibility for this to happen is to say that v1 is equal to v2. Okay, so which we know that it really is not going to make much of a sense, but that's the only option that we have to enforce the velocity 0. Now the second idea is when we have the cusp. In the case that when we have the cusp, v1 at the top, v2 at the bottom, in this case, you're seeing that these are parallel to each other. So therefore, we know that these are not equal to, the velocity has to be the same because, and the values itself are not equal to 0, but the difference between velocity top and bottom have to be 0. This is just the consequence of the Kutta condition that says that your circulation around the stagnation at that stagnation point has to be a single value and it has to be equal to 0. In this case over here, what happened is neither one of these velocities necessarily, they are not parallel to each other. Okay, they are not parallel to each other, and I need the velocity to be equal to 0. So therefore, the only option, I cannot say v2 minus v1 is equal to 0, because they, in general, they can be a different value when this happens. So in such a case, we have no choice in taking this equal to 0. So in this case, the Kutta condition, it is satisfied. We can say v1 is equal to v2. Couple of things we keep in mind. First of all, we are saying the value of the circulation is such that it's going to leave the edge, the trailing edge smoothly. So what we are saying, the Kutta condition is saying that it's going to leave the edge smoothly. So you have v1, v2, such that your gamma is equal to 0. You can say that v2 minus v1 is equal to 0. Okay. Second thing is saying if the trailing edge is finite, the trailing edge is a stagnation point. So this is finite, right? It ends there. So we want this to be a stagnation point there. It has to be a stagnation point. So if this trailing edge in the cusp, and then the velocities are leaving the loop, and the top and bottom of the edges are equal in magnitude. So that means that v1 is equal to v2. And these are the consequences of the Kutta conditions as applied to airfoils, the aerofoil analysis. So you have a case where you have 0 lift flow in a case like this. So you have no circulation here, so you have no lift, and your flow is coming here, so therefore it goes there. But when you do have lifting, that means that you have rotation, you have a circulation, and that circulation is saying that has to leave this edge completely smoothly. Okay, that's what it really means. So this concludes our discussion on the theory of thin wall, thin airfoil Kutta condition.